Hi everyone, welcome to One Stop Mathematical Solution. Today we are going to solve CSIR NET Mathematics December 2014 question paper. In this video we have only dealt with the complex analysis part. First we'll look into the part B question. Question 22. Let k be a positive integer. The radius of convergence of the series sigma n is equal to 0 to infinity n factorial whole power k by kn factorial z power ns. They are given a power series here. We have to find its radius of convergence. We'll look into the concepts used. Consider the power series sigma n is equal to 0 to infinity an z minus z0 whole power n. Then the radius of convergence of this power series is given by the formula 1 by r is equal to limit n tends to infinity modulus an plus 1 by an, or you can use the formula limit n tends to infinity modulus an power 1 by n. Now we will move on to the question. So they are given this power series here. So here the coefficient an is equal to n factorial whole power k divided by kn factorial. So 1 by r is equal to limit n tends to infinity an plus 1 by an. So substitute the an plus 1 term, that is equal to n plus 1 whole factorial into whole power k divided by k into n plus 1 factorial divided by an term and factorial whole power k divided by kn factorial. I am taking this whole term to the upper side. So this is equal to limit n tends to infinity n plus 1 factorial whole power k into kn factorial divided by k of n plus 1 factorial divided by n factorial whole power k. Now I am rearranging this term so that this is equal to limit n tends to infinity n plus 1 factorial whole power k divided by n factorial whole power k into kn factorial by k of n plus 1 factorial. Now I am expanding those factorial terms. So this is equal to limit n tends to infinity 1 into 2 into etc. up to n into n plus 1 whole power k divided by 1 into 2 into n whole power k into 1 into 2 into etc. up to kn divided by 1 into 2 into etc. up to kn plus 1 etc. up to kn plus k. After removing the same terms, we are getting this is equal to limit n tends to infinity n plus 1 whole power k into 1 by kn plus 1 into kn plus 2 etc. up to kn plus k. So from this denominator I am taking n common from each term. So there are k terms here, k n terms here. So we will get like this is equal to limit n tends to infinity n plus 1 whole power k into 1 by n power k into k plus 1 by n into k plus 2 by n etc. up to k plus k by n. Now again I am rearranging this term so that we will write this as equal to limit n tends to infinity n plus 1 whole power k divided by n power k by into 1 by k into 1 k plus 1 by n into k plus 2 by n etc. up to k plus k by n. So here the powers are same, so I can write it as it is equal to limit n tends to infinity n plus 1 by n whole power k into 1 by k plus 1 by n into k plus 2 by n etc. up to k plus k by n. Now I am multiplying the now I am dividing the numerator by n separately. So this is equal to limit n tends to infinity 1 plus 1 by n whole power k into 1 by k plus 1 by n into k plus 2 by n etc. up to k plus k by n. Now I am applying the limits. So when n tends to infinity 1 by n is tending to 0. So all this term is tending to 0, this term is tending to 0, this term is tending to 0, this term is tending to 0. So we will get 1 into 1 by k into etc. up to k times. So this is equal to 1 by k power k. So therefore we got 1 by r is equal to 1 by k power k, that is r is equal to k power k. So this is our radius of convergence. So we will check the correct option. So the correct option is third one. Next question, question 33. Let P of Z is equal to A0 plus A1Z plus etc. up to ANZ power n, and Q of Z is equal to B1Z plus B2Z square plus etc. up to BNZ power n be complex polynomials. If A0, B1 are non-zero complex numbers, then the residue of P of Z by Q of Z at 0 is. So they are given two complex polynomials P of Z and Q of Z. We have to find the residue of P of Z by Q of Z at 0. We look into the concept used. If f of z is analytic at z0 with f of z0 not equal to 0 and g of z has symbol 0 at z0, then the residue of f of z by g of z at z0 is equal to f of z0 by g prime of z0. G prime is the derivative of g of z whose value is found at z0. If f of z is equal to z minus z0 whole power m into phi of z, where phi of z0 is non-zero, then f of z has 0 at z equal to z0 of order m. Now we'll move on to the question. So they are given the polynomial P of z and Q of z like this. If you see that P of z is a polynomial, so it is entire. So in particular it is analytic at 0, and we are getting P of 0 is equal to A0, and A0 is given to be a non-zero complex number. So the first condition is satisfied here. So we'll check for the denominator. Here denominator is Q of z, so it should have a symbol 0 at 0. So we'll check that. So if we check, Q of z is equal to B1Z plus B2Z square plus etc. up to BNZ power n. I'm taking z common, so we'll get this is equal to z into B1 plus B2Z plus etc. up to BNZ power n minus 1. So if I take this bracket as the function phi of z, we should get phi at 0 should be non-zero. So phi of 0, we are getting it is equal to B1, and B1 is non-zero number. Therefore, phi of 0 is not equal to 0. Therefore, Q of z has 0 at z equal to 0 of order 1. That is, Q of z has a symbol 0. So we can use this formula for finding the residue of P of z by Q of z at 0, which is equal to P of 0 by Q prime of 0. We got P of 0 as A0, and Q dash of z is equal to B1 plus B2Z plus etc. up to NBN z power n minus 1. Therefore, Q dash of 0 is equal to B0. So the value is equal to A0 by B1. So this is the residue's value. We'll check the correct option. So the correct option is first one. Next question, question 34. Let sigma n is equal to 0 to infinity an z power n be a convergence series such that limit n tends to infinity an plus 1 by an is equal to r greater than 0. Let p be a polynomial of degree d. Then the radius of convergence of the power series sigma n is equal to 0 to infinity p of n an z power n is. So they are given a convergence series which satisfies this condition and a polynomial of degree d. Then we have to find the convergence of this power series. We look into the concept used. Consider the power series sigma n is equal to 0 to infinity an z minus z0 whole power n. Then the radius of convergence of this power series is given by 1 by r is equal to limit n tends to infinity an plus 1 by an, or limit n tends to infinity modulus an power 1 by n. Now we will move on to the question. So given a convergence series sigma n is equal to 0 to infinity an z power n such that limit n tends to infinity n plus 1 by an is equal to r, which is greater than 0. And p is a polynomial of degree d. I am taking here it as p of z is equal to z of degree 1. Let radius of convergence of z n equal to 0 to infinity p of n z power n be r dash. So using the formula 1 by r dash is equal to limit n tends to infinity an plus 1 by an. Here the coefficient an is p of n into an. So n plus 1 will be p of n plus 1 into n plus 1 and an divided by an, that is p of n by into an. So I had taken p of z is equal to z. So p of n plus 1 will be n plus 1 and p of n will be n. So this is equal to limit n tends to infinity n plus 1 divided by n an. So I am rearranging this so that this is equal to limit n tends to infinity n plus 1 by an into an plus 1 an. This can be split into two limits. So this is equal to limit n tends to infinity n plus 1 by n, limit n tends to infinity n plus 1 by an. So when we apply this limit, I am getting it as 1. When we apply this limit, I am getting it as r. So 1 by r dash is equal to r. Therefore, r dash is equal to 1 by r. So this is the radius of convergence of the series. So we'll check the correct option. So the correct option is first one. Now we will move on to the part C questions. Question 80. Let u of x plus iy is equal to x cube minus 3xy square plus 2x. For which of the following functions v is u plus iv a holomorphic function on C? So they are given a function u. We have to check for which of the option u plus iv becomes a holomorphic function. So we look into the concepts. If f of z is equal to u plus iv is analytic, then ux equal to vy and uy is equal to minus vx. These two equations are called the CR equation, that is the Cauchy-Riemann equation. If ux, uy, vx, vy exist and are continuous and satisfy CR equations, then f of z is analytic. Now we will move on to the question. So given u is equal to x cube minus 3xy square plus 2x. Now I am finding ux, that is partially differentiate u with respect to x. So that is equal to 3x square minus 3y square plus 2. And uy, which is the partial differentiation of u with respect to y, that is equal to minus 6xy. So we have to check for which of the options we are getting ux equal to vy and uy is equal to minus vx. Here I have only done two options, that is the first two options. You guys have to check for the rest of the options. So first option, v is equal to y cube minus 3x square y plus 2y. So first I am finding vy, that is partial differentiation of v with respect to y. So that is equal to 3y square minus 3x square plus 2. So if you see that we are not getting ux equal to vy, that is vy is not equal to ux. So this implies that u plus iy cannot be a holomorphic function. So this option cannot be happening. So second option, v is equal to 3x square y minus y cube plus 2y. So first I am finding vy, partial differentiation v with respect to y, that is equal to 3x square minus 3y square plus 2. So we are getting ux equal to vy. Now we find vx. Vx is the partial differentiation of v with respect to x, that is equal to 6xy. So we are getting here uy is equal to minus vx. So it is satisfying Cauchy-Riemann equation. Therefore, u plus iv is becoming a analytic function, that is a holomorphic function. So the second option is correct. Similarly, you can check it for the third and fourth option. So they are not going to satisfy the CR equation. So the correct option is second one. Next question, question 81. Let f be an entire function on C. Let g of z is equal to f of z conjugate whole conjugate. Which of the following is or are true? So they are given an entire function f and a new function g is defined based on f. Then we have to find which of the option is true. So we'll check the options one by one now. So if f of z belongs to real number for all z in R, then f is equal to g. So we'll check that condition. So if z belongs to R, then we know that z is equal to z conjugate. So this implies f of z is equal to f of z conjugate. Take conjugate on both sides. So this implies f of z whole conjugate equal to f of z conjugate whole conjugate. And we know f of z is a real number. So this implies f of z conjugate equal to f of z. So replace this conjugate by f of z. So this implies f of z is equal to f of z conjugate whole conjugate. and we know this is defined by g of z. So this implies f of z is equal to g of z, that is f is equal to g by identity theorem. So this option is correct. Next option, if f of z belongs to R for all z in Z such that imaginary Z equal to 0, union Z such that imaginary Z equal to A for some A greater than 0, then f of Z plus IA is equal to f of Z minus IA for all Z in C. So we'll check this option. Now f of Z belongs to R for all Z in Z such that imaginary Z equal to 0, union Z such that imaginary Z equal to A. So this can be written as f of z belongs to R for all z equal to x or z equal to x plus I a. That is f of z belongs to R for all z equal to x or z minus IA equal to x. Now if f of z belongs to R, we are having f of z is equal to f bar of z. So I am applying it for z minus IA. That is f of z minus IA is equal to f of z minus whole bar. So z is a purely real number, so I am taking it conjugate. So that is equal to f of z bar minus IA whole bar. So z bar minus IA can be replaced as z plus IA whole bar. So this is equal to f of z plus IA whole bar, the whole bar. And we know this is equal to g of z plus IA, and we know by first option g of z is equal to f of z. So this is equal to f of z plus IA. Therefore we got f of z minus IA is equal to f of z plus IA. So second option is also true. Third option, if f of z belongs to R for all z in z such that imaginary z equal to 0, union z such that imaginary z equal to A for some A greater than 0, then f of z plus 2IA is equal to f of z for all z in C. So this first condition is same as the second option. So by 2 we have f of z plus IA is equal to f of z minus IA. Now if I replace z is equal to W plus IA, then we have f of W plus IA is equal to f of W plus IA minus IA. That is f of W plus 2IA is equal to f of W. So we have this condition here as the same. So this option is also true. Fourth option, if f of z belongs to R for all z in z such that imaginary z equal to 0, union z such that imaginary z equal to A for some A greater than 0, then f of z plus IA is equal to f of z for all z in C. So we will check this option. So if I take f of z is equal to e power z plus pi I, that is this is equal to e power z into e power I pi. We know e power pi i's value is minus 1. So f of z value is minus e power z. So f of z plus I pi I am getting is equal to e power z plus pi I plus pi I. That is e power z plus 2 pi I. So this can be written as equal to e power z into e power 2 pi I. So e power 2 pi I value is 1. So this is equal to e power z. So if you see that if you take A is equal to pi, we are not getting f of z is equal to f of z plus I pi. So this option is wrong. So now we'll check the correct options. So the correct options are 1, 2 and 3. Next question, question 82. Let f of z is equal to sigma n is equal to 0 to infinity, a n z bar n be an entire function, and let r be a positive real number then. So they are given a function here. We have to check which of the following option is true. So we'll check the options one by one. So f of z is equal to sigma n is equal to 0 to infinity, a n z bar n an entire function, and r is a positive real number. So I am defining a function like that. So f of z is equal to 1 plus z square. So this is a polynomial. We know polynomials are entire function. So here a0 is equal to a0, a1 is equal to a2 is equal to 1. That is coefficient of each term. And an is equal to 0 for all n greater than or equal to 3. And I am taking r is equal to 1. Now we have sigma n is equal to 0 to infinity mod an square into r power 2n is equal to for this case, for this function, this is equal to sigma n is equal to 0 to 3 mod an square into 1 power 6. Here all an's are 1, so this is equal to mod 1 square plus mod 1 square plus mod 1 square, that is equal to 3. For this case, we are getting sigma n is equal to 0 to infinity mod an square r power 2n equal to 3. So keep it like that. Now consider mod f of z, which is equal to mod 1 plus z square. So by the modulus property, this is less than or equal to 1 plus mod z whole square. And mod z, I am taking it is equal to r here. So r is here 1. So this is equal to 1 plus 1 plus 1, that is equal to 3. So we got mod f of square is less than or equal to 3 square, which is equal to 9. So taking the supremum, so we'll get supremum mod z equal to 1. Mod f of z square is equal to the highest value, which is equal to 9. So we are getting sigma n is equal to 0 to infinity mod an square r power 2n is less than supremum of this. But supremum of this is not less than sigma n is equal to 0 to infinity mod an square r power 2n. That is 1 is correct option but 2 is incorrect. Now check 1 by 2 pi integral 0 to 2 pi mod f of r e raised to I theta whole square d theta, where I am taking z is equal to r e raised to I theta. So f of r e raised to I theta means in this case 1 plus r e raised to I theta plus r e raised to I theta whole square. So this is equal to 1 plus r e raised to I theta plus r square e raised to 2 I theta. Here I have taken r is equal to 1. So f of e per I theta is equal to 1 plus e per I theta plus e per 2 I theta. Now we will find this value. So before that I am finding the modulus of f of e per I theta's value. So this is equal to modulus of 1 plus e per I theta plus e per 2 I theta modulus square. I know modulus z square can be written as z into z conjugate. So using that we will write like this. And taking conjugate means conjugate can be split. So that is written in this step. And we know one conjugate is 1. E per I theta's conjugate is e per minus I theta. And e per 2 I theta conjugate is e per minus 2 theta. So substitute that, we'll get this step. Now multiply each brackets. So we'll get like this equation. Now simplify these terms. So this is equal to 3 plus 2 e raised to I theta plus 2 e raised to minus I theta plus e per 2 I theta plus e per minus 2 I theta. Now find the integral value 1 by 2 pi integral 0 to 2 pi modulus f of e per I theta whole square d theta. So substitute this value here. So this is equal to 1 by 2 pi I integral 0 to 2 pi 3 plus 2 e raised to I theta plus 2 into e raised to minus I theta plus e power 2 I theta plus e power minus 2 I theta into d theta. So integrated separately, applied the limits. So finally we are getting the answer 1 by 2 pi into 3 into 2 pi, that is equal to 3. So we are getting the third option as correct and fourth option is incorrect. So we will check the correct options. 1 and 3.